All right, let's dive right in. We are going back, and I mean way back. Not to the dinosaurs, not to the formation of Earth, but to the very first, almost unimaginable moment of the universe itself. This is, without a doubt, the ultimate cosmic mystery, a time before time as we even know it. And the story of how we even began to get a grip on it? Well, it starts with a truly spectacular failure. Picture this. It's 1999. NASA is on the verge of these huge success with its Mars Climate Orbiter. This thing was going to be the first ever interplanetary weather satellite, mapping the Martian climate. So after a 10-month journey, it starts its final approach to Mars. And then, nothing. Just radio silence. The orbiter is gone. Vanished. A $300 million ghost. So what on Earth could have happened? A catastrophic failure? An asteroid? Nope. The investigation found the culprit, and it was almost laughably simple. A units mix-up. See, NASA's team was using the metric system, meters, kilograms, but an outside contractor who built a key part used the same numbers but thought they were in feet and pounds. That tiny, tiny error sent the orbiter burning up in the Martian atmosphere. It's a crazy reminder that if you don't have a standard, absolute way to measure things, you get chaos. And believe it or not, that exact same idea is our key to unlocking the universe's very first moment. To really understand the cosmos, we need a ruler that isn't based on us. We need a system of measurement that any alien civilization on the complete other side of the galaxy could figure out. We need a cosmic standard. I mean, just think about our units for a second. An inch? It's roughly the breadth of a thumb. A kilogram? That's the mass of 1 liter of water. An hour? It's just a totally arbitrary slice of one single spin of our particular planet. Out in the vastness of space, these are completely meaningless. There are no thumbs, there's no water to weigh, and an Earth day means absolutely nothing. So how in the world do you quantify the universe objectively? This is where the absolute genius physicist Max Planck comes into the picture. Around the turn of the 20th century, he had this incredible idea. He said, what if we just use the laws of nature themselves as our ruler? Things like the speed of light or the force of gravity. Those constants are the same everywhere, for everyone, all the time. By combining these cosmic rules, he created a set of truly fundamental units, Planck units. And these units are, well, they're impossibly small. Take the Planck length. This is basically the fundamental pixel of our universe. You physically cannot have a distance smaller than this. It's not just a tiny number, it is the absolute limit of smallness. And time? Get this. If you take 1 second, just one tick of a clock, the number of Planck time units that fit inside that single second is greater than the total number of seconds that have passed since the Big Bang. That's the universe's shutter speed. It's the shortest possible moment that can exist. So why do these mind-bogglingly small units even matter? Because they let us define the final frontier. They let us ask the question, what was the universe like when it was just 1 Planck length across and 1 Planck time old? This first instant, this is what we call the Planck era. And it's basically a lawless Wild West where our entire understanding of physics completely shatters. To understand why our physics breaks down, we have to talk about the 2 towering achievements of the 20th century. 2 brilliant theories that describe our universe perfectly, but they absolutely refuse to work together. In one corner, you have Einstein's general relativity. This is the law of the very large. Planets, stars, galaxies, the whole shebang. It describes gravity as the smooth, curving fabric of space-time. And in the other corner, you have quantum mechanics. That's the law of the very small, atoms, electrons, photons. It describes this bizarre, probabilistic world where particles can be in 2 places at once. Both theories are incredibly successful, but they are fundamentally, totally incompatible. And what's wild is that they kind of grew up separately. You had Newton, who gave us our first real take on gravity. Then Einstein comes along and completely rewrites the rules for the big stuff. And at almost the exact same time, you have physicists like Heisenberg diving into the weird quantum world, discovering a whole different set of rules for the small stuff. For decades, these 2 ideas just ran on parallel tracks. Which, of course, brings us to the ultimate collision point. What happens when you have something with the entire mass of the universe, which absolutely needs general relativity, but it's crammed into a space smaller than a single proton, which means it needs quantum mechanics? Well, that is the Planck era. It is the one place in all of history where these 2 sworn enemies are forced into the same tiny room. And this right here is the holy grail of modern physics. It's the quest to find a single theory that can finally unite them, a theory of quantum gravity, a theory of everything that can finally tell us what in the world happened in that very first moment. So let's meet the leading suspects in this cosmic investigation. One idea is a particle called the graviton, a tiny messenger that would carry the force of gravity, kind of like how a photon carries light. Then there's loop quantum gravity, which says space-time isn't a smooth sheet, but more like a fabric woven from tiny, plank-sized loops. And of course, there's the famous one, superstring theory, the idea that everything at its core is made of these impossibly small, vibrating strings. They're all brilliant ideas, but for right now, they're unproven. And here's why they're so hard to prove. To see things on a Planck scale, to actually test these ideas, you would need a particle accelerator larger than our entire solar system. Yeah, so for now, that's just impossible. We have to rely on pure theory and imagination. So using that imagination, armed with our best theories, what does the Planck era actually look like? What is our best guess for what the universe was like in its very first chaotic instant? Probably the best description we have comes from the physicist John Wheeler. He came up with this amazing analogy. He said, imagine looking at the ocean. From far away, the surface looks smooth, right? But if you get right up close, you see this chaotic, bubbling, seething mess of foam. Wheeler proposed that space-time itself is just like that. At our scale, it looks smooth, but zoom all the way into the Planck scale, and it's a chaotic, roiling quantum foam. So what does that mean? Well, first off, it means that first moment was fundamentally totally unpredictable. The rules of logic that we depend on hadn't even been written yet. And that leads to this, the most basic law of our reality, that an action causes a reaction, that one thing leads to another. It just didn't exist. There was no before to cause an after. Just think about that for a second. Instead, what you have is this reality where space-time is constantly folding and twisting in on itself. Tiny little microscopic black holes and wormholes are bubbling into existence and then vanishing in an instant. The very fabric of space is in this constant, violent, random flux. The source material for this explainer put it perfectly. It's like trying to run a horribly corrupted simulation. The universe is glitching, it's flickering, it's writhing, as the laws of physics are trying to load for the very first time. And because of that absolute randomness, we can't look back any further. The Planck era is a fundamental wall in our knowledge. Trying to know what came before it is impossible, because the chain of cause and effect that defines history hadn't even started yet. And that leaves us with a truly mind-bending thought to wrap up with. We've just explored the moment that space and time literally burst into existence from we don't know what. But if they had a definitive beginning, a moment when the rules were born out of pure chaos, does that imply that they could also have an end? And what would that even look like? That's a question that pushes right to the very limits of what we can even imagine.